on this computer. Okay, we're going to continue on with chapter 11. It's all about alcohols and the reactions of alcohol. Remember, we learned how to make alcohols in chapter 10. Okay, so, and we also learned how to make alcohols in chapter 6. So that's going to be on the all reactions. You're going to see those are not going to be duplicated in my all reactions table. In chapter 11, I'm just going to say see chapter 5, see chapter 6, and see chapter 8. But what we learned yesterday was the fact that we could now take our alcohol and turn it back into an alkyl halide. Now, this would be very useful if you only had an alcohol laying around and you wanted to do other different reactions with it, especially when we go on to the next chapter 13 and 14, where we get to learn that Grignard reagent. We'll want to have, that's another way to make alcohols, but we have to start with our alkyl halides first. So we learned that we can do with just HCl, HBr, HI, those are all strong enough acids to convert secondary and tertiaries to alkyl halides. But the chloride was not good enough to do the primary alcohol by itself. The HBr and HI can, so we had to make oxygen a better leaving group. This is the theme for the rest of this chapter, making oxygen a better leaving group, okay? Because OH is a horrible leaving group, right? It's a really strong base, and therefore it's not a good leaving group. So how can we make oxygen a better leaving group? Well, make it not OH. So the first thing we did was we add acid, it leaves as water. That made it a better leaving group. But chloride is not a strong enough nucleophile to displace just water. So we made a bond between zinc and oxygen, and that bond between zinc and oxygen now made oxygen a better leaving group. It's no longer water, it's actually physically bound to the zinc. And then a good SN2 reaction, this is even a better leaving group than it was before, and we're allowed to do that, okay? So we can do it with HBr and HI because they are better nucleophiles. And if we look at our nucleophile chart, if we go back to chapter 6, bromine and iodine were good nucleophiles, chlorine and fluorine were fair nucleophiles. So chlorine is only a fair nucleophile, so we have to take something else to make it a better leaving group. Okay, so how else can we make it a better leaving group? Well, the key here is going to be reacting oxygen with something to make it a better leaving group than even water. Okay, so our next thing is to convert our alkyl halides to chlorides. This is a better reaction because it'll take any of these primary and secondary alcohols, and with the compound SOCl2, which is called thionyl chloride, it's got 2 chlorines to transfer, but it's only going to transfer 1. Okay, so what we're going to do here is we're going to make a sulfur oxygen bond. Okay, we're going to make a sulfur oxygen bond, and so this is a sulfonyl ester right here, and this sulfonyl ester has already liberated a chloride ion. Okay, but to make it a good leaving group, we're actually going to use a base. In this case, this is a base, Lewis base. It's going to pull a proton off and give us our neutral sulfur compound. Now we can come in with our nucleophile because we have a better leaving group. And when it kicks out, it's going to make SO2, which is a gas, and chloride ion, which is going to be able to be used as a nucleophile. Okay. So the key here is this sulfur oxygen bond is stronger than the hydrogen oxygen bond, and therefore it makes it a better leaving group. And we get rid of the material, we get rid of that oxygen in the process. Excuse me. Okay, so this is a great way to make alkyl chlorides. We only use thionyl chloride. We typically don't have the chloride or the bromo version or the iodine version. So this is great for making primary or secondary. Why can't we make a tertiary? It's an SN2 reaction. It's an SN2 reaction. This is just a leaving group. We have to hit it with an SN2 reaction. Therefore, we can only do it in primary and secondary. Okay. So what's another way of making it into a better leaving group? Turns out phosphorus is what we call oxophilic, meaning it loves oxygen. It wants oxygen. In fact, in its best perfect state, like in our DNA, It actually has 4 oxygens around it and makes these phosphate esters with our glucose to help bind all our DNA together. That's its favorite place to be, is having oxygens around it. So what we're going to do is we're going to take the OH here, and we're going to take either, we can do it with phosphorus tribromide, okay, or we can actually make the iodine version in situ. It's not actually stable, but we can make it in situ. We can make it in the reaction, which is in situ. Okay, so what we're going to do is we're going to take the phosphorus here, and it is acting as a Lewis acid. Our electrons are acting as our Lewis base, and we're going to make a new bond here. Okay, so now we have this phosphorus oxygen bond, which is stronger than the carbon oxygen bond, and we can now, with our good nucleophile, displace this, giving off our phosphorus with our oxygen on the end. In fact, it'll do it multiple times, and we'll end up with phosphoric acid out of it. We can actually transfer all 4 of these bromines off. All 3 of these bromines, so we don't have to use them. So this works on primary and secondary alcohols for the exact same reason. It's an SN2 reaction. Okay, it's an SN2 reaction, but the first step is reacting our Lewis acid with our Lewis base to make it into a good leaving group, making displacement of that oxygen easier. Okay, questions on that? So we're making sulfur oxygen bonds, which make them good leaving group. We're making phosphorus oxygen bond, which makes them good leaving group. Okay. So we can do it, and if you look in the book, you can do it with iodine, but you have to use the a phosphorus compound plus iodine to make it in the reaction. All right, so this is a review of everything we've learned so far. We're using acid to make OH a better leaving group as water. We're using acid as OH leaving group as water. We try to use acid, but chlorine's not a good enough nucleophile. So we're helping it along with the Lewis acid. Okay, we're making it a better leaving group here. Now we can do it with phosphorus or chlorine. I'm sorry, bromine or chlorine using that phosphorus compound. And it again is making that phosphorus oxygen bond, is making it a better leaving group. And then the last one is that sulfur oxygen bond, making it a better leaving group. And again, all of these are SN2 reactions. Right here, when these can actually do these can do SN1 reactions. They can actually form our leaving group. But it's mostly primary and secondary alcohols. Okay, continuing on with this theme, we're going to turn something into a better leaving group by reacting it with a sulfuric acid derivative. Okay, so sulfuric acid is a very strong acid, right? So when it's displaced, it's a very weak base, making it a good leaving group. Remember, good leaving groups are very weak bases. The weaker the base, the better the leaving group. Okay, so in this case here, we're going to do from what we call a tosylate. And on the exams, it's going to be labeled as OTS. That's a tosylate. Okay, that's making your oxygen a good leaving group. Okay, and so if we draw the structure here, tosylate means toluene sulfonic acid. So this part is toluene, this is a sulfonic acid, and so this is a toluene sulfonic acid ester. Okay, so we call that a tosylate. Anytime you see AIT at the end, think ester. Remember that osmate we made? That was the osmium ester. Tosylate, this is the sulfonic acid ester. Ethyl acetate, that's an organic ester. Okay, so we're turning it into this sulfonyl ester, and we do a reaction first. You can actually make this ahead of time and isolate it and purify it, and then hit it with any nucleophile you want. Okay, so what we're going to do is we're going to react this to give you this, and then we can turn it into these leaving groups. And again, the abbreviations are TS, or the ester is whatever alkyl group you have plus OTS. Okay, so to make these, all we have to do is start with a sulfonyl chloride. This is paratoluene sulfonyl chloride, or tosyl chloride, or TSCl. You're going to see that as the reagent, and they're going to add something like base. The most common base we're going to use is pyridine. What it's going to do is it's going to react with this, and it's going to kick out HCl. Okay, it's a nucleophilic attack. And then we'll actually have that. You can isolate it and purify it and everything like that. Okay, so why is this toluene sulfonic acid derivative such a good base? Well, the same reason sulfuric acid is a good base, resonance. Okay, it has resonance structures that allow that charge to be spread out over 3 atoms, over those 3 oxygens and a little bit over that sulfur, right? So it's a really poor base, therefore it's a really good leading group. Okay, so now that we have that on there, all we have to do is we can use it in both SN2 and E2 reactions, depending on whether you're hitting with a good nucleophile, SN2, a good nucleophile. In this case, we're using the methoxide, right? What's wrong with methoxide here, though? It's also a good base. So we want to probably do this a little bit cooler. And what it's going to do is it's going to do an SN2 reaction on the carbon with the tosylate on it. And then we're going to kick out that, and we're going to have, in this case, an ether. Okay. So what if we used a strong non-nucleophilic base? We're going to have to find a beta hydrogen. And we're going to have to do an E2 elimination. Okay, we're not, again, this is primary. We're not going to form a carbocation. So it's SN1 and SN2 and E2 only. SN2 and E2 only. And then when in this case here, we can use it as a leading group to give us our alkene. Probably not the best use of atoms because you're putting on this huge group and then turning it into something very small. Okay, so that's an atom economy where it's not very good. Here, we're still, again, not very good, but sometimes you have to do it because that's the only way it's going to work. Okay, again, the tosylates are removed by SN2 reactions and E2 reactions because they are displaced by good nucleophiles or bases. But you don't have to rely on just that toluene sulfonic acid. We actually have a bunch of derivatives. One derivative just has a methyl group there. We call that the mesylate, methyl mesylate. Mesyl group, alkyl mesylate right here. The only thing we changed was this. It's no longer benzene, so it's nice and small. And so we don't have as much waste, and we don't have as much mass loss in our material. And then, of course, we have the tosylate. And then we also can put a trifluoromethyl group here. What that does is that pulls electron density around through induction and makes it an even weaker base. It's going to make it a stronger acid, but it's going to make it a weaker base. So all 3 of these can be seen in your textbook. MSO is the methyl sulfonic acid. TSO is our toluene sulfonic acid. And TF or TFO is our triflate, trifluorosulfonic acid. Trifluoromethane sulfonic acid. All right. But notice the structure is the same. All we're doing is making that OH a better leading group. Okay. So this is kind of an overview of ways to convert your alcohol. We can convert our alcohol with sulfuric acid or POCl3 to give us an alkene. Basically, we're doing an E2 reaction. We're eliminating our alcohol and a beta hydrogen and giving it set. Or we can convert it directly to the alkyl halide and then use it to do something else. Okay, so this is kind of looking at multi-step synthesis here. We're going to start with an alcohol, convert it to an alkyl halide, and then convert it to something else with either an SN2 reaction for the nucleophile or an E2 reaction for the alkene. And then we can do the same thing with making it the tosylate, where once we make the tosylate, it's isolable. This is isolable. And then we can convert it either by an SN2 reaction or an E2 reaction to other things. So you can convert any alcohol into an alkyl halide or a tosylate or some other sulfonic acid derivative. And then you can do E2 or SN2 reaction. In focused E2, you want to use the big base. You want to use T-butoxide if you want to do the elimination reaction. And then if you have a primary and secondary, you can do a good SN2 reaction. Questions on that? Okay, so what if you wanted to do a reaction, like let's say you wanted to extend the chain of your alcohol. You have a alkyl halide on one side and alcohol on the other side, and you want to do, you want to add an acetylene to it, right? So if you deprotonate that acetylene, that turns it into a very strong base. Okay, so we have our acetylene, we add our sodium amide to make our acetylite ion. And then the first thing that acetylite ion is going to do is it's going to react with the hydrogen here, because this is more acidic than the acetylide hydrogen was, and therefore it's going to deprotonate here and the reaction's going to stop. Okay, nothing's going to happen. In fact, what might happen is that this might just come over here and displace this and make a ring. That wouldn't do any good at all, right? So what we want to do is we want to protect the alcohol by just making it non-protic. So we want to take that hydrogen off, make some other oxygen bond, and then do the chemistry on the one side. But the key about protection is you want to be able to clip it off. Okay, so you want it to be good for a lot of different reactions, but you want to have some little like a trick to clip it off. And that's what we call protection deprotection strategies. This is used a lot in multi-step synthesis, by the way. Okay, so in this case here, what we're going to use is we're going to use this T-Butyl protecting group. Now, the reason this T-Butyl is a really good protecting group is because it's really big, and so it's not susceptible to being displaced by nucleophiles. Number two, it's an ether. Ethers are very poorly reactive. So we're going to see that those don't react very much. And then, so when we do this, we're going to take our material here. This is isobutylene, and then we're going to hit it with acid. What's that going to do? Well, that's going to turn it into a carbocation. And then this is going to be our nucleophile to hit our carbocation, and that gives us our group here. So now we have this ether. It's very low reactivity. So now we can take our material and do our reaction to make our acetylite ion to get our nucleophile, act as a nucleophile here to get to our product here. But now we have to clip it off. We did it here with sulfuric acid and isobutylene with no water or very little water. We're trying to drive it to the carbocation, right? So to reverse it, what we're going to do is we're going to do acid-based hydrolysis. And the reason that this is going to fall off so easily is because that T-butyl group can form a carbocation. So we're going to end up protonating this and allowing it to come off as a carbocation. What kind of solvent promotes carbocations? Polar protic solvents. We have it in water. It's going to support that carbocation. It's going to turn back into isobutylene. And we're going to gain our proton back. I'm sorry, it's going to be display, it's going to turn it into T-butanol. Because there's so much water around, you're forming the carbocation, the water is going to react with it to give us T-butanol. Okay, so this is the first protecting group we can do. And it's called the T-butyl ether group or ether protecting group. Okay. And it's easy to put on with acid without water. Do your reaction, easy to remove with acid with water. Okay, so the other thing you can do is make a silicon oxygen bond. Okay, and that's even better because that has very low reactivity as well. And the way we do that is we take a silicon group here with, at least 3 different carbon groups on it, and then one chlorine. Okay, so it can be trimethyl, but some people really like this dimethyl T-butyl because we have the T-butyl is a really big group that protects that silicon and that oxygen from reaction. So we are not going to have any SN2 reactions happening here. And so we use a base, and this base is used as imidazole, and we use a non-polar protic solvent, which is DMF, to encourage our SN2 reaction to form our silicon oxygen carbon bond. Okay. Now the coolest thing about that is then you can do all the same chemistries that you can do on any other thing, and as long as you don't do it with a strong acid, or silicon has a special property. It really loves fluorine. So to remove it, all you need to do is have something with a fluoride ion. In this case, it's T-butyl ammonium fluoride. So the 4 bonds to nitrogen, and it gives it a formal charge of +1. And then we have our fluoride ion. And that fluoride ion is so aggressively wants to attack that silicon, reactions are done in 10 minutes. Just stirring in some kind of solvent. In this case, it's THF. Okay. So this is another strategy for protecting them, but it's a very clean strategy. What we're going to see is that we're going to see this TDSO, or sometimes it'll be TMS, trimethyl silane. You might see that on your homework. Okay, so I said that we have to use very strong acid to clip those ethers off, right? So let's talk about that. There is the possibility of doing this, but it takes 2 equivalents of acid. One has to act as a deprotonating agent. One has to act as a nucleophile for one side, and it'll give you an alkyl halide. And then the one will act with the other side, giving you another alkyl halide if it's unsymmetrical. If it's symmetrical, it'll give you 2 equivalents of the same alkyl halide. So let's look at this. It takes a total of 2 equivalents of acid because one of the acids is going to be consumed making the first alkyl halide. The second equivalent of acid is going to be used to make the second alkyl halide. Okay. And we can use HBr, HI. HCl is not strong enough. HCl is not strong enough. It's HBr or HI. Now, because we have to hit it with this very strong acid at very high temperatures, we tend to make ethers our go-to solvent for polar aprotic solvents because they are very non-reactive. Diethyl ether, THF, and dioxane. There's 2 others that we are going to look at here are dimethoxyethane. Occasionally it's called lime. That's an old engineering name. I don't know why. And then this one right here, T-Butyl methyl ether. Now, the thing about T-Butyl methyl ether is it's actually an additive in gasoline. It has a kind of a sweet smell. Unfortunately, it's environmentally persistent because it's hard to cleave the ether. So they're actually phasing it out and they're using more things like ethanol. Okay, so ethers are hard to cleave unless you hit them really hard with strong acids and a lot of heat. Unless it's an epoxy. Okay, so let's look at the mechanism here. Obviously, the first thing we're going to do is we're going to protonate the species to make it a better leaving group. So it's going to kick out as an alcohol right here. And then in this case here, we're going to form a carbocation, which then is going to react with the iodine we just created. Then the second one is going to happen to the other, whatever the alcohol was, and we're going to exchange the alcohol, just like we did before converting an alkyl halide. We're going to protonate it first, then we're going to hit it with a nucleophile, and that's why we end up with that. So we actually end up with 1 equivalent of water because we had 1 oxygen, and the 2 hydrogens come from the 2 equivalents of acid. The 2 halides come from the 2 equivalents of acid. Questions on that? So it's going to be a stepwise thing. We're going to protonate the system. We're going to hit it with a nucleophile and an SN2 reaction here. But because this is tertiary, this is an SN1 reaction. Okay, so this is our SN1 reaction because we formed the carbocation. And then we're going to do it again. Questions on the mechanism of ether cleavage. And again, this is that methyl T-butyl ether that I was telling you about on the end of the chart on the last page. Okay, so we have reactions that we can do. It's not easy, but we can clip our ethers. We can use them as solvents in a lot of different reactions, and we can protect our alcohols, and we can make our oxygens better leaving groups now. Okay, so what can we do next? Well, let's talk about that special little ether. Okay, this is the one ether that's easy to clip. This is the one ether that's easy to do because of ring strength. It wants to pop open. So if you hit it with a nucleophile, it's going to spring open and we're going to be able to use it in the reactions. Okay, so there's a couple ways to make these. The first way is the Williamson ether synthesis. You have an alcohol and a halogen in the alpha and beta positions, what you can do is deprotonate this alcohol, and then it is going to wag around here, and eventually it might come in and act as its own nucleophile and kick out the halogen. So in this case here, we're starting with a halohydrin, oxygen, OH and a hydrogen. And we know how to make halohydrin, right? We can take an alkene with HBr iodine in water, and that'll make the halohydrin. So in a multi-step synthesis, they're going to say, turn this alkene into an epoxy. Well, you don't have to do it this way. You could do in two steps with the halohydrin reaction: alkene, halohydrin, and then deprotonation to give you an SN2 Williamson. Or you can use a new reagent. This new reagent is a per carboxylic acid, PER, carboxylic acid. What that means, it means it has one extra oxygen in it, just like a peroxide, where it has one extra oxygen, but we're going to do a per acid. Wait, didn't we already use a per acid? Didn't we use metachloro perbenzoic acid already? No, we haven't used that yet. Oh, I guess it's on the next slide. Anyway, so we have this per acid. What's going to do is it's going to transfer one of these two oxygens. And I'm going to tell you it's this one. And I know it's this one because this oxygen is partially positive and this oxygen is partially negative. And I'll show you that. And what's going to happen is going to basically add across the double bond, giving you a carboxylic acid and our epoxy. Now, if you look way over to the far right lower thing, there's a structure drawn for metachloro perbenzoic acid, or MCPBA. In your homework, it's going to say MCPBA. On your exam, it's going to be MCPBA. What that means is you have a per acid, which means you're going to make an epoxy. Okay, so you'll want to make sure you write that down, memorize that. In your reaction table, you're going to have epoxies two ways: Williamson ether synthesis with a halohydrin and perbenzoic acid with an alkene. Okay, so let's look at the mechanisms of that. So the mechanism for this right here is just an SN2 reaction, and that's fine. But the per acid one is kind of weird. Okay, so if we actually started to look at where electrons are being transferred, this oxygen here is partially negative because of its proximity to this carbonyl. This one turns out to be partially positive. So it is our Lewis acid. It is our electrophile. Now, our double bond here are electrons out, not in between two atoms. So it is the nucleophile. So we have a reaction with a nucleophile and electrophile, and we move 1, 2, 3, 4, 5. 5 pairs of electrons get moved all at the same time. Because you only get one product, you only get the epoxy. So you're going to move 5 pairs of electrons all at one time, and you're going to end up with your carboxylic acid and your epoxy. Remember, oxygen-oxygen bonds are very weak, and we can use those. But this is not a radical reaction. This is a concerted nucleophile reacting with an electrophile. Okay, so let's talk about the chemistry of it. It's always syn addition, because it's going to be on one side or the other. It can attack the top or the bottom. So that gives you stereochemistry that you can see, okay? So in the case of this, let's talk about this. This is what is this? Is this cis or trans? A cis alkene. So our cis alkene, if we attack from the top, it's going to give one isomer. If we attack from the bottom, it actually gives us an enantiomer. Because if you flip it over, the ethyl group is going to be on this side, and the methyl group is going to be on that side. So they are non-superimposable mirror images of each other. So they are enantiomers. So you're always going to get a mixture you can't control. So the stereochemistry is going to give you the cis alkenes, give you those cis substituents. That's also how we know it's a concerted reaction, because there's no rotation. The trans alkenes are going to give us trans substituents. Again, no rotation happened all. All right, so now that we have our rings, what can we do with them? Well, it turns out we can do two different things. We can just have a good nucleophile, and that'll open it one way, or we can actually have an acid catalyzed with a not so good nucleophile. So let's talk about that. If we have our epoxy here, we're going to have this side, notice, has two methyl groups, and this has two hydrogens. So one side is sterically hindered. Okay, it's like a tertiary carbon. The other side is a primary carbon. Okay, so the two different mechanisms are going to specify which carbon gets hit. Now, in this case here, remember, we start numbering with the oxygen. So this is 1, 2, 3. So this is the 2 carbon with the 2 methyl groups on it. Okay. If we have a good nucleophile, it's going to attack the less hindered carbon, making your alcohol on the tertiary carbon. In this case, what was the 2 carbon is now the 1 carbon. So we attacked it on the less substituted side, giving your alcohol on the more substituted side. We see that alcohol is what was the epoxy, and the nucleophile is on the other carbon now, the beta carbon, in this case, the less hindered carbon. But if we use acid and a poor nucleophile, we get the other way around. The nucleophile attacks the more hindered carbon, and we have the alcohol on the less hindered carbon. So using the same reagents almost, we can make the primary alcohol or the tertiary alcohol by changing the reaction conditions. So this is going to be 2 different reactions on your reaction table. Okay, so one has a strong nucleophile, one has a weak nucleophile, but an acid catalyst. Okay, so if we just have a good nucleophile, our good nucleophile is going to attack the less hindered side because it's a primary carbon. Nucleophiles will always attack the less hindered carbon if possible. Okay, so we're just going to have, in this case, a good nucleophile, sulfur with electrons here. It's going to kick in here, kicking up these electrons, giving us the anion. And then something is going to be around where we can get a proton from it. Okay, so that's going to give us our tertiary alcohol and our primary attack where our nucleophile is. Okay, so that's pretty good. So we have to have good nucleophiles like OH, RH. Notice all of these are anions except for nitrogen. Nitrogen's the cool one because it's lone pair. It's actually satisfied, even though it's neutral, it's as a good, reasonable nucleophile, fair nucleophile. It's not a good nucleophile, but it's a fair nucleophile. Look back at your table. Now, why do I bring up the nitrogen? Okay, so when the most common way that you have used epoxy is squeezing a little tube with 2 little gels in it, right? And if you squeeze it in, the one that's clearer is the one with the epoxy in it. And the one that's yellower is the one with the amine curing agent. Okay, so one's going to actually smell kind of good. It's going to smell kind of like a nail salon. And then the other one is going to smell stinky, like bad fish. Okay, that's the one with the amine. Okay, and so the amine is going to act as a good nucleophile and attack this and open it up. Okay, so now let's look at the mechanism of the acid catalysis. So if we're acid catalyzing something, the first thing you're going to do is you're going to protonate something. And the oxygen still has lone pairs on it, so we're going to protonate the oxygen first. Okay, when we do that, we get this oxonium cation, right? We've already formed oxonium cations before. In this case here, we now have 2 different carbons. 2 different carbons. One carbon's tertiary and one carbon's primary. Okay, so what it's going to do is it's going to make the tertiary carbon more partially positive because we have a positive charge on oxygen. It's going to dump electron density up to that oxygen that's positive charge. And we have the possibility of forming a partially positive charge on a tertiary carbon. or a partially positive charge on a primary carbon. So where is it going to go? The tertiary carbon. So our nucleophile is going to attack our tertiary carbon, leading to our primary alcohol. Okay, so that's why they are different. When you have a good nucleophile, you end up with the alcohol on the more substituted side because your nucleophile is attacking the less sterically hindered. When we have an acid catalyst, we actually end up with a nucleophile on the more substituted side because this is more substituted and can carry more of a partially positive charge, making it a better target for our incoming nucleophile. Now, because it's partially positive, we can actually use weaker nucleophiles, but that's true. Okay, questions on the opening, acid opening of our system. So the epoxy that you have is actually the first one, the good nucleophile, nitrogen good nucleophile.
What if both carbons are the same number of the carbons?
Then it'll be symmetrical no matter what. You can't tell. Yeah, but that's a great question. The only way you can tell is if you had a cis or trans epoxy, because then you're going to have enantiomers because it'll probably attack half the time one and half the time the other if they're sterically the same. Or electronically the same too, because they would be both secondaries or tertiaries. I imagine that you would actually slow the reaction down because of that. Okay. So, oh, that's interesting. If we attack with water in acid, we could get a diol, a 1,2 diol, 2 alcohols. Okay, so we're able to do a cis diol by using the osmium tetroxide. It gave a syn addition, and then we reduced off the osmium and we got to the syn addition. Okay, so that's one way to do it. But what if you wanted the trans alcohol? That's where the epoxy comes in, because the oxygen is sitting on one side and you're always going to attack from the other side from where the oxygen is. So you're always going to get the trans diol. Okay, so now we have 2 ways to get to diols are, in this case, cold permanganate or the osmium tetroxide. Both of this gives syn addition. So we can get the syn, or we can convert our alkene to an epoxy and then react it in acidic water and we'll get the trans. But again, it's going to give us because it's trans, it doesn't have a mirror plane and we're going to have enantiomers. These only give 1 isomer each, right? Because we have a mirror plane here, we have a mirror plane here. So we only have 1 meso compound in each of those. This gives us enantiomers. Okay, and the whole reason it does is that if the OH is down, we're going to protonate it, and the water has to attack this or this. So if it attacks this one, it's going to give 1 enantiomer. If it attacks this one, it's going to give the other enantiomer, but they're both going to be trans. They're both going to be on opposite sides of the line. All right, questions on that? Okay, because that's the last slide. That's the last reaction in chapter 11. Okay. All right. So I have a challenge for you. So I'm gonna start the review tomorrow, but I have a challenge for you. I want you to see how many of these reactions you can get. Bring your reaction tables, because I'm going to do an activity, a multi-step synthesis activity tomorrow in class, using your reaction tables to figure out who. And some of them are going to be long. Then I'm also going to do an activity that involves what I call a spider activity, which is I'm going to put a reagent, I'm going to put a reagent in the middle, the starting material. I'm going to put the products around the outside, and I want you to pick the reagents. This is a great study tool because you don't focus on the substrate. You focus on the change. Focusing on the change is one of those things that I asked you to do on the filling out. Know your reaction forward, know your reaction where you pick out the middle, and know the reaction where you pick up the starting material. I'm going to give you those activities, and then I'll post in fact, I'll give you the key afterwards so that you can use that as a study guide. Okay. So again, we're gonna do those two activities plus a review of 1 through 5 tomorrow. And then we're gonna do 6 through 11. And I will show you, and yeah, I'll show you the all reaction table tomorrow or Thursday. Now I'll show it to you tomorrow so you have plenty of time to finish it. Okay, and then we have our exam at 11 a.m. on Friday.
Do you have any like test questions from chapters 10 and 11? Example questions?
I will post my chapter 10 quiz and my chapter 11 quiz. Yeah, you definitely need a chance to look at it. Okay, also, if you don't already have one, get an ACS study guide. The newest version actually has first half, second half. And they word things a little differently, and it'll get you familiar with the way they word things.
The newer one's the orange one. The newer one is the orange one.
So, I had one like three things ago, so it's not very good. They didn't have it when I was here, when I was going through this. Class. But, all right, so go ahead and do that. I will post 11 and 10, quiz 10 and 11 today. So you can get some chances, and then we'll do those reviews and those activities, okay? All right, and then I will have that all reaction stuff ready for you. All right. I like having a small class because you feel like they're okay. So, any other questions? Okay. Worry a little bit about the exam. Worry enough to make you study, but not enough to make you sick. Okay. Just make you study, but not make you sick. Okay. Now, the exam has 70 questions. You're going to look at some questions and go, and that's fine. And that's fine. I mean, the average raw score is about 50%. My classes tend to be 55 to 60%. By the way. Anyway, because I'm making reaction. It helps. And then my best score I've ever got was 60 out of 70. They were brilliant anyway, but we never studied. Just kind of walked. But it is possible. That's in the 97th percentile, by the way. If you want, I will tell you what your raw score percentile grade was nationally. Just email me and say, what was my percentile? I'll give it to you. But it will be, I report a raw score to the department, but you will have a curve score based on how well the class did as a whole. I'm kind of sad I didn't get wear a kilt this year. But
So what if we get above 75 on the final?
then I'll just break a bottle of wine with my kilt.
But that is resumed.
Yes. Maybe. So. But. How many kilts do you? At least. All right. All right. Again, study tonight. Review tomorrow, study tomorrow night, review. And then come in well rested. Water, if you like caffeine, do it. If you have ADD, use your caffeine or your meds. If you have anxiety, use your meds. Use box breathing. You're gonna see stuff and it's okay. But you're gonna be prepared for next semester. My whole goal is to prepare you for next semester. So you don't walk in and go, I don't know any of this stuff. I can't do any multi-step synthesis. Okay. If I let you go through without learning this, then you're just going to be, wasting your time and have to take the second half. So that's my goal, is to get you very well prepared for that. Okay. All right. Thank you very much. I'm going to stop recording and stop sharing and look for posts.